Welcome to our fifth and final electrochemistry video. We're going to focus on concentration cells first. A concentration cell is a cell based solely on the electromotive force generated because of a difference in concentration. So what's in the name? Whoa, wow, what is that word? Concentration. Starting off well. All right. So a voltaic cell, which is what we've been doing, cells that are able to run without any extra energy added in, a voltaic cell can function if it has the same species at the anode and cathode. So if it has nickel at the anode and nickel at the cathode. What must happen though is that you must have different concentrations, because once the concentrations are equal, it stops working. In this system, always, if the E of the cell is 0, then the system would be at equilibrium and the cell would be dead. When you're doing calculations using the Nernst equation, the E standard is always going to end up being equal to 0. Here we have this equation times the log of Q. Because we have the same substance on both sides, so bleep bloop, that's gone. So I guess what we really should say is once the concentrations are equal, the cell will be dead. When the concentrations of electrode 1 and electrode 2 are equal, then this cell would be dead. So E cell, not standard, regular E cell, can be positive if the concentration at the anode is less than the concentration at the cathode. So if E cell is positive, is that thermodynamically favored or non-thermodynamically favored? That is thermodynamically favored P process. So if the anode has a lower concentration and the cathode has a higher concentration, that should be positive when you calculate the E of the cell. As the reaction proceeds over time, the concentration of the anode will increase, so we'll get more and more anode. This will increase, 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 and we'll get less and less of the cathode until eventually their concentrations are equal, and then it will stop working. So let's do a problem. We have a voltaic cell with solid nickel electrodes. So these are our solid bars of nickel, and it operates with 1.5 molarity nickel 2 plus at the cathode. So I have 1.5 molarity nickel 2 plus at the cathode and 0.0015 molarity nickel 2, that should be a plus sign, at the anode. And we have to figure out E of the cell. So remember, E cell, is this at standard conditions? I mean, we don't have 1 molarity, so no, it can't be standard. But we do have 25 degrees Celsius, so I get to use that simpler version of the Nernst equation, Nernst, which is 592 over N, where N is what? What is N here? N is the moles of electrons transferred. Okay, in order to figure out Q, we have to figure out which concentration is going to go up top and which one will go on the bottom. They're both nickel 2 plus, so that makes it a little bit harder to figure out. So what I'm going to do is, let's see, I'm going to try to write a net ionic. I'm going to write my anode equation and my cathode equation. I'm going to add them together. So I have nickel solid. Ooh, I'm going to regret making this so small. Nickel 2 plus aqueous diluted. Yeah, that's the one that has the lower concentration, so I'll write that down here just so I can keep track. It's a 0.0015 and it's aqueous. Plus 2 electrons. And then the other one is nickel 2 plus, but this one is the concentrated one, which is 1.5 molarity. That plus 2 electrons reacts to form solid nickel. So usually when I go to cancel things out in a net ionic, anything that looks the same gets canceled out. So like my electrons, they go away. And my solid nickel, that gets canceled out too. However, these two nickel 2 pluses are different because their concentrations are different. And so that's actually what's left behind in my net ionic. I will have Ni2 plus 1.5, that's what its concentration is, reacts to form Ni2 plus, and this one is 0.0015. So that helps me figure out Q, because I know that Q is products over reactants. So let's go ahead and just start plugging stuff in. I know that the standard cell potential for a concentration cell is equal to 0. Oops. Over N. How many electrons are being transferred between the two here? Looks like 2 electrons times the log of Q. Products over reactants. Looks like this is my product based off my net ionic, and that's my reactant. All right, so you plug this all in, and you should end up with positive 0.089 volts. So, is this thermodynamically favored or not? This is a thermodynamically favored process. That means it happens spontaneously, and I know that because it's positive. All right, this is a longer one. A voltaic cell is constructed with 2 hydrogen electrodes. 2 of them. So if they're both hydrogen, that means that this must be a concentration cell. Electrode 1 has a pressure of 1 atmosphere for H2 and an unknown hydrogen concentration. Electrode 2 is a standard hydrogen electrode of 1 molarity concentration for H plus and 1 atmosphere pressure for the hydrogen gas. At 298 Kelvin, the measured cell voltage is 0.211 volts, so that's my E of the cell. And the electrical current is observed to flow from electrode 1 to electrode 2, so that means electrons are going from here to there. We need to figure out the concentration of hydrogen for the solution at electrode 1 and figure out the pH. Oh my gosh, this is impossible unless you draw it out. In my opinion, I think it makes your life easier. So keep this slide in front of you so that you can reference it. I have to switch to a different slide though. All right, so let's draw it first. I have my 2 half cells. They both have hydrogen electrodes that are connected to each other by a wire. This is electrode 1, this is electrode 2, and they're telling us electrons are flowing that way. Okay, so if electrons are flowing to the right towards electrode 2, does that mean that electrode 1 is being oxidized or reduced? It is being oxidized because it is losing electrons. It's losing them to number 2. So this is being oxidized. Does that, well, I'll write that on here. Oxid. And this one must be being reduced. So that means this is the cathode and this is the anode. So I'm going to use that then to write my half reactions. So for what's the oxidation half reaction for hydrogen? It needs to be losing electrons. It would be H2 gas reacts to form 2H plus 2E minus, and this one will just be the reverse, 2H plus 2E minus. Ah, room is nice. H2 gas. All right. We have some more information. They told us about pressures. They told us that the pressure of the first electrode of hydrogen, so the pressure of my H2 at electrode 1 is equal to 1 atmosphere. They told us the pressure of H2 at electrode 2, this is a terrible way to write this. Here, let's do that. Is also equal to 1 atmosphere. That's nice. And what else? The concentration at electrode 2, they told us. The concentration of my hydrogen ions is equal to 1 molarity. And the goal is to figure out the concentration at electrode 1. Okay, well, let's just kind of start plugging things in and see what happens. I have my Nernst equation. E cell is E standard minus, this is at 298 Kelvin, so I again get to use my handy dandy shortcut. Okay, so we know E standard is 0 in a concentration cell, and they told us the E of the cell earlier is 0.211 minus 0.0592. How many electrons are being transferred between the two? 2 times the log of Q. Okay, this is the hard part. Let's figure out Q on the side over here. I know Q is products over reactants. And like we've never actually mixed pressures and concentrations because it doesn't really work that way. Unless you have a concentration cell where notice how these pressures are both for H2. The ratio of these pressures is equal to the ratio of their concentrations. Let me write that. The ratio of the pressure of hydrogen in cell 2 to pressure of hydrogen in cell 1 is equal to the ratio of the concentrations of these guys. So as long as I use pressures for both hydrogen gases, then it doesn't matter if I mix them in with the concentrations of the other ones. So let's write that out. That means that I'll have, I should probably have a net ionic in order to do this. So let's write that down. I'm going to add these two equations together. The electrons get canceled out. I'll have H2 of electrode 1, which is, here, I'll write gas 1. Let's do it like that. Plus 2H pluses, and this is aqueous from cell 2. Reacts to form 2H pluses aqueous cell 1 plus H2 gas from cell 2. If you are confused right now, you might want to pause and track where all these came from up here. Make sure you know why that turned into this. So you should pause and figure that out. Okay, so welcome back if you paused. So now I know my products and my reactants. I'm going to write out my Q equation. So I'm going to use the concentration of my hydrogen ions from cell number 1. It has a coefficient. That's right. And then the pressure of my hydrogen gas, which is in cell 1. No, that's a 2. Cell 2. And then I'm going to use the concentration of my hydrogen ion from cell 2, and this one is also squared times the pressure of my hydrogen gas. This one's in cell 1. So that's products over reactants. Woo-wee. So let's plug this in then. It'll be 0.211 is equal to negative 0.0592 over 2 times the log of, let's get all these numbers. I'll put little check marks to what we know, because they're all 1, the ones that we know. We know this one, and this one, and we're solving for the leftover. So the hydrogen ion concentration in cell 1 squared times 1 over 1 squared times 1. Okay, well those are all 1s, so forget that. So now I get to solve for the concentration of my hydrogen ions. So if I multiply some stuff out, I'll end up with negative 7.128 is equal to the log of the hydrogen ion in cell 1 squared. Remember, if you want to get rid of logs, what do you have to do? You do 10 to the 10 to the. Those cancel out. I'm also going to have to take the square root of both sides here. 10 to the negative 7.128 is equal to the number that I want squared. So I have to square root both sides. And this will get you your answer. 2.73 times 10 to the negative 4 molarity. Wow, that was long for this unit. You're going to have to practice this. You're going to have to practice. Okay, let's move on to something completely different. Let's talk about electrolysis or electrolytic cells. So voltaic cells are the ones that happen automatically. Galvanic, voltaic, whatever, they happen automatically. Electrolytic cells do not happen automatically. They are non-thermodynamically favored. And they force these reactions to happen by sending electrical energy through the cells. So it's also called electrolysis. So electrolysis is when electricity causes a chemical change. It requires a source of direct electrical current hooked up to the two electrodes. So if you have your two electrodes in here, and they're connected, you need to have some sort of something over here. That has to be a source of electrical current. So you have to remember that the anode takes electrons from one species in solution, and then the cathode will give electrons to another species in the solution. So we have losing versus gaining. Okay, here we have the electrolysis of molten NaCl. So we're going to have this yellow stuff in here represents melted sodium chloride. So sodium chloride, it's ionic. Does it take a really low temperature or really high temperature to melt it? Really, really, really high temperatures. So it's hot, 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 hot. And these electrodes then are made of something else, maybe platinum, I'm not sure, something that won't melt when sodium chloride is melted. And then we have our source of direct current here, and it's supplying this electrical energy that is kind of kick-starting the flow of electrons. So it is forcing the chlorines that are in the chlorides that are in solution, it's forcing them to give away those extra electrons. It becomes a solid or a gas. In this case, they become a gas. And those electrons move through, and then they join up with the sodium here, and what it does is causes liquid sodium to show up. So we had sodium ions, they took on these electrons, they went, ooh, electrons for me? Sure, I'll take one. And then it leaves liquid sodium behind. That's pretty cool. This does not happen automatically. You need that source of direct current in order for this to happen. All right. During the electrolysis of an ionic aqueous solution, either the positive ion can be reduced or water could be reduced. So when you're using electrolysis for an aqueous solution, so it's got something that's water is mixed in there, it's not necessarily the positive ion that's reduced. Like in the last situation here, sodium was reduced. However, if this was aqueous, water might have been the one that was reduced. It just depends on the reduction potentials. So in the same way, either the negative ion can be oxidized or water can be oxidized. These statements, I believe, are exactly the same. So let's just doop, doop, doop. That didn't happen. If a substance cannot be oxidized any further, then water will be oxidized instead. So let's say you have a solution that has positive ions and water, but the positive ions are the ones that get reduced. Once we run out of those positive ions, then water kind of like picks up where it left off and it starts being reduced. Or it could be the other way around with oxidation. All right, so we're going to compare these two guys' reduction potentials to determine which one's more likely to be reduced or oxidized. So if you want, you could pause this and look on your chart for the reduction potentials yourself to practice looking those up. You might want to pause if you're going to do that. All right, if you're not looking it up on your own chart, here you go. This one is negative 0.83 volts, and the other one is positive 1.23 volts. So, between the two, which one is more likely to be reduced? This one is more likely to be reduced. So that means that this one is probably going to be oxidized. All right. Okay, well, what if we have calcium iodide in solution? We have calcium iodide in solution. It's aqueous. That means we have calcium ions floating around, we have iodine ions floating around, and we also have water in the mix. So what you do is you compare, first you take the positive ion. Okay, reduction could either be a positive ion or water. It's not going to be the negative ion. So compare your positive ion to water's reduction potential. And there's more than one equation for water on your charts. You might notice that. It's going to be the one that involves hydroxide. For reduction, use the one that involves hydroxide. Just going to have to memorize it. So for this, which one is more likely to be reduced? The one that's more positive is more likely to be reduced. So in this case, even though I have calcium in there, it's not going to get reduced. Water will be reduced instead. Weird. Oxidation could be a negative ion or water. So calcium was not an option for oxidation. It has to be a negative ion. Or it could be water. So here we'll compare these two equations. We'll compare the iodine one, and we'll compare the water one that involves it splitting into oxygen gas and hydrogen and electrons. So we're going to compare their reduction potentials here. Go ahead and ignore this bottom part for now. Just compare their reduction potentials. Which one is more likely to be oxidized? The number that is more negative is more likely to be oxidized. So this one is more negative, or you could say it's less positive. That's probably a better way to say it. Less positive. Now this phrase down here, this is actually referencing oxidation potentials. These are reduction potentials. So this phrase is separate. Don't link it to the numbers that are above it. The species that has the most positive or least negative oxidation potential is oxidized. So if for some reason you have oxidation numbers instead, you want to look for the one that's the most positive, because that means it's more likely to be oxidized. More positive, so more positive means more likely to be oxidized. So I don't know, that confuses me. I prefer to just think of it in terms of reduction potentials, and then I don't have to start like being like, is this oxidation or is it reduction? Which way does it go? I don't know. So let's have another example with a drawing. Here is our aqueous calcium iodide. So you can see that based off of our last set of questions, the iodide is being oxidized. It's losing electrons. And the water here is being reduced. That should be what we had. Let's go back. Whoops. Yep, there it is. Water is being reduced. Whoops. And iodine is being oxidized. So this is because of their reduction potentials. And this is really only happening because we are sending a electrical force through it. A source of current is there. All right, now what if we have the electrolysis of aqueous copper 2 bromide? Let's practice problem. A direct current is applied to an aqueous copper 2 bromide solution. Here are a bunch of equations. First we have to figure out the reduction half reaction, then the oxidation half reaction, then the overall reaction and delta G. Don't panic, you'll be fine. So, for reduction, what are our options? Can it be a positive ion, a negative ion, or both? It has to be a positive ion or water. So we're only going to pay attention to the positive ion, copper, and water. And remember, for reduction, we're going to deal with the one that turns into hydroxide. So here it is, this one. All right, so out of these two numbers, which one is more likely to be reduced? Looks like copper wins this time, so copper is going to be reduced. All right, this guy's out of the running now. You can ignore it. Now let's compare the other two. We're going to compare this version of water being reduced and the negative ion, because for oxidation we're dealing with the negative ion, or H2O. So out of these numbers, which one is more likely to be oxidized? The number that is less positive is more likely to be oxidized. So that would be bromine. So this one's out of the running. So you can actually completely ignore those other equations. They don't even matter anymore. They're gone. We don't care about them. So we need to write our overall reaction. So we're going to add these together. Is this already balanced? Are the electrons balanced? Well, they're both 2. That's good. I have this one written as reduction. The bromine, though, is still written as reduction, so that's actually not good. We need it to be written as oxidation. So what do I have to do to this equation? I have to flip it. So let's write this again before we add them together, because otherwise this is going to get funky. Plus 2 electrons, copper, solid. Okay, flip the bromine to Br minus. Reacts to form Br2, and it's a liquid. Whoa, that's an L. Plus 2 electrons Of course, the L is the largest thing here. Oh well. Okay, now we can add these together. Now our electrons cancel out. Phew. So our final answer will be copper 2 plus 2Br minus reacts to form solid copper, oh man, plus Br2 liquid. Okay, that's my overall reaction. Now we have to figure out delta G. I'm going to need more room for that. So let's go on to the next slide. You keep this one in front of you. I'll write my equation up here. Oops. So copper 2 plus 2Br minus copper solid plus Br2 liquid. Okay, so we need to figure out delta G. This is electrolysis, so why don't we use something that has a standard cell potential in it? We have an equation for that. You could look at your formula sheet, I believe, to get this. All right, N, what does N stand for? Moles of electrons transferred. What does F stand for? Faraday's constant. Which you'll want to memorize as 96,500 coulombs per moles of electrons. And then E standard. There's a formula for that. E standard, you calculated this today in class. Well, not today anymore. It was a Wednesday. It's the E standard reduction of the what minus the E standard reduction of the what. So what minus what? Cathode minus anode. Okay, so we have to get these from the previous slide. I want my two numbers, 1 and 2. And I'll do cathode minus anode, cathode minus anode. So it'll be dang it, I am not doing well at that today, 0.34 volts minus 1.07 volts equals negative 0.73 volts. Ooh, a negative. Does it make sense that this one would be negative? Yeah, it should, because they're using electrolysis to make it happen, which means, they had to use electrolysis. So it didn't happen on its own. It is non-thermodynamically favorable. Okay, cool. So now I think we have everything we need to find delta G. Standard. How many electrons are transferred between copper and bromine? There are 2. Negative 2. Okay, Faraday's 96,500 coulombs per moles of electrons. Okay, times this number I just got, negative 0.73 volts. Okay, you know what? Let's back up. What's another way to express volts? What are volts? What per what? Joules per coulomb. So I'm going to put that here because that's going to help me figure out what my units of G are. So G is going to come out to 140,000 what? Joules per mole. Joules per mole. Okay, so, well, let's convert that to kilojoules. 140 kilojoules per mole. All right, I think that's it. That's that one. Does it make sense that it's positive if this is non-thermodynamically favored? Yeah, It's positive. For Gibbs free energy, negative means spontaneous and positive means not. So this one is non-thermodynamically favored. So check, it makes sense. They're both non-thermodynamically favored numbers. Wonderful. Okay, last one. How long would it take to place out 3.56 grams of silver from a solution containing silver ions when a current of 2.5 amps is applied? All right. Let's think back to amps or amperes. Those are also known as coulombs per second. This is a handy thing to know. So let me show you what we can do. Let's take our 3.56 grams and we're going to try to convert it into time, and this is going to factor in there somewhere. So first let's convert it into moles because grams are pretty much useless to us in conversion problems. Sorry grams, nothing against you. Okay, now I want to get this to have coulombs be involved. Let's think. We've got what uses coulombs? I know Faraday's constant does, which is 96,500 coulombs per moles of electrons. Can I convert moles of silver into moles of electrons? Yeah, I definitely can. So if I was to write out the net ionic for this, I know that silver solid could turn into positive silver plus how many electrons? It gave up 1 electron in order to become plus 1 silver. So look at the coefficients. 1, 1, 1, 1, 1, 1, 1, all ones. Okay, cool. I've canceled out electrons. Well, let's use Faraday's constant now to get coulombs. Hopefully you see where we're going now. 96,500 coulombs per mole of electrons. And I know I have 2.5 amps, which means I have 2.5 coulombs per second. So let's cancel out coulombs. But I want minutes, so let's convert from seconds to minutes. 60 seconds in 1 minute. And voila, you have converted grams into time. How crazy is that? You've converted mass into time. I think that's pretty cool. So you end up with 21 minutes if you multiply that all out. And this actually has a practical application, believe it or not. You know how people like to have silver plated spoons? This is how they, once they figured this stuff out, this is how they would do it. So they would take a bar of silver, which they could get, they get a bar of silver, and they put it into solution, and they connect it with a battery, something that's going to supply that current, and it forces the silver to come out into ions. They hang a spoon down the other side, and those ions, they pop off of the solid bar of silver, and then they rejoin again back onto the silver spoon. So you end up with a silver-plated spoon. How cool is that? All right, congratulations. You have made it through all the notes. Now it's time to practice.